Well, good morning, everyone. To kick off today, we have Chada from Heriot University, who will be talking about unbiased kinetic Langevin Monte Carlo. And I look forward to the pronunciation of Yububu.
I've already said it. Yeah. Okay, hello, good morning, everyone. Thank you to James for the introduction and the invitation to speak here. Today, what I'm going to be presenting is to speak up just a little bit. Okay, sure. Today, what I'm going to be presenting is very recent work, which is based on a general theme or area of sampling. So as many of you know, Markov chain Monte Carlo is the gold standard technique which is used in order to sample from distributions of interest. More recently, a very nice direction in this field has been on the development of unbiased estimators related to MCMC, or sampling from distributions. The reason for this is because depending how you set up your MCMC method, there are a number of biases that can naturally arise from this. So a lot of this recent work has been done by Pierre Jacob, based on a very nice work by Rhee and Glynn going back to 2011. What we are going to do in this presentation and in this work is to develop a new methodology for unbiased estimators, which alleviates a lot of these issues related to the biases and also the metropolization step, which I will discuss later on, which is based on the simple notion of discretizations of the kinetic-based Langevin stochastic differential equation. And so what I'm going to show you in this presentation is by considering this, we are able, as I've mentioned, to alleviate some of these issues. And I'm going to show you through both theoretical and numerical experiments that we can indeed get good results and are competitive with gold standard MCMC methods, such as the randomized Hamiltonian Monte Carlo method. And so with this leads to the title of today's discussion, which is Unbiased Kinetic Langevin Monte Carlo. So this is joint work with a number of individuals, Ben, Daniel, and Peter, who are all in the audience. So when I give a presentation, I always like to give a motivation to what I'm doing and why I'm doing it. As I've already alluded to, the main emphasis of this presentation is focused on sampling from distributions of interest. In particular, the aim of this presentation, if I can find the pointer, is that we are interested in developing unbiased estimators of this quantity that you see right here, which is the expectation of f, which is a pi integrable function with respect to some distribution that we're interested in sampling from. Now, if anyone is familiar with sampling from distributions or Markov chain Monte Carlo methods, the general way that you would actually write the aim of this in any textbook or lecture note is given by this equation that you see right here. So the expectation of f with respect to the target distribution of interest that you're interested in sampling from is given by this. So in essence, it's an integration problem. So for many years, people have decided to actually consider traditional numerical analysis techniques that can actually solve this problem, but there are a number of issues that can arise from this, such as dimensionality and also intractability. So a very nice idea that came about in order to solve this problem was to simulate an ergodic Markov chain whose invariant distribution should be the distribution of interest. In other words, the distribution that you're interested in sampling from. And this is known as MCMC and utilizes well-known statistical theorems, such as the central limit theorem, as well as the strong law of large numbers. Despite this, even though it all sounds very good, and it is very good, as I mentioned, there are a number of issues that can arise from this. And some of the issues, not all of them, some of the issues are given as you see right here. The first issue that I've stated is what I refer to as the MCMC bias. So for any of you who is not familiar with MCMC bias, just to give you an idea from this, I think this is the best way to explain what I mean. So I'm giving you an experiment where the target distribution of interest is given by a standard normal distribution. In other words, the mean is 0, the variance is 1, and what I do is that I set an initialization distribution, which is known as the prior. The prior that I've set for this experiment is given by this. It's quite different, it's from the same family, but the point is that the mean and the variance are slightly different. And as you can see, the initializations essentially start from here because the mean is 10, so they'll probably be based around here. And what we want to do is to learn the target distribution, which is centered at 0. Well, as you can see, through these different simulations, these Markov chain simulations, what happens after a particular time iteration is that we start to reach stationarity, for a lack of a better phrase. And with this, what you can see is a particular time interval for which it takes to learn this particular region. And this region that you see right here is known as the learning period. And so this is what I refer to as the MC. So that's one of the particular biases that can arise from MCMC. As well as this, depending on how you actually choose your sampler or proposal, there can be a discretization bias in the case if you use a continuous-based sampler, such as MALA or IF. As well as this, related to MCMC, there can be scalability issues related to how you choose the acceptance probability related to the dimensionality, as well as learning multimodal distributions. So what I hope to show you from this presentation is that we can overcome some, if not most of these issues through the simple technique of exploiting kinetic Langevin methods, which can hopefully handle all of these issues. Okay, so in essence, that is the motivation, what we are interested in doing from this presentation. Okay, and again, this is the MCMC bias, which arises from this period, which is known as the burn-in period. Okay. So I'm going to move on straight to the actual methodology that we're going to use for this paper, which is based on the kinetic Langevin dynamics. So this is a coupled set of differential equations where V of t is governed by this stochastic differential equation that many of you would be familiar with, which is known as the underdamped Langevin dynamics. From this equation, there are a number of terms which interest, such as gamma, this term here, which is given as the friction term. And we also have this usual Brownian motion, which corresponds to the noise that we have within the system itself. And this underdamped Langevin dynamics is pretty interesting because it has an invariant measure or stationary distribution, which is given by this. So if anyone is familiar with the overdamped Langevin dynamics, where you just have a single equation which looks very similar to this, you would essentially ignore this v squared norm over 2 term, and what you would have is this invariant distribution instead. Okay, so this is almost like an extended version of the overdamped Langevin dynamics, and it has a number of interesting properties or advantages to why one would consider this. Unfortunately, I only labeled one. I thought I labeled a number of advantages, but there are more than one advantage of using this. One of this compared to the overdamped Langevin dynamics is that it does have faster convergence rates. As well as this, it also has very good connections with well-known MCMC methods such as Hamiltonian Monte Carlo. So actually, this set of equation that you see right here has seen a lot of attention recently in the machine learning community. I think a lot of work has been done on this related from Peter Bartlett and also Michael Jordan and other related co-authors, where they've looked at both, I believe, non-asymptotic and asymptotic results related to this methodology as well. So this methodology is seeing a lot of interest and traditionally has also been looked at in the fields of molecular dynamics as well. So it's a very well-known set of equations or stochastic differential equation. And this is the exact methodology or equation that we're going to use to present our unbiased estimate. Of course, if we're interested in doing this in terms of an implementation, one has to discretize the system. And as Des mentioned at the very beginning, the most basic form of discretization one can consider is the Euler-Maruyama scheme. What we are going to consider are more advanced schemes compared to the Euler-Maruyama to ensure we get potentially a better weak error or a better strong error. And what we're going to use is this notion of splitting schemes. So as it says at the very top, the key idea behind these schemes is to split the dynamics into parts which can be integrated exactly. And one well-known splitting scheme that you can consider is what I refer to as the BAO splitting scheme. So in other words, you have your kinetic Langevin stochastic differential equation here, and what you do is that you split it up into various components. These components are given by A, B, and 0. And so what we do with this is that we integrate each part exactly, which is just given through these set of equations that you have right here. And so if you are interested in actually setting up a discretization scheme based on these split and order methods, you can come up with very nice palindromic schemes which read like this. For example, this is the easiest one to pronounce, which is Obabo, and this is Baob. So these have very interesting names. And the idea behind this of why they have different letters or why there are different number of letters is that in this example, you have 2 B steps, 2 A steps, and 1 O step. So for the first B step, we solve this using a step size of h over 2. And similarly for A, we also do this for h over 2. And because we only have one step of 0 or O, it means we solve this with h. So that's what I mean when we have 2 of these letters and 1 of these letters. And commonly, you will see this in a palindromic form. So these are just 2 particular examples that you can consider. What is very interesting about Obabo, just to give you a particular case, is that for Gaussians, this works exactly, as well as having a weak order of 2, but it only has a strong order of 1. So at least compared to the Euler-Maruyama scheme, it has more favorable properties if you're interested in implementing this. What we are going to consider is an alternative splitting scheme, which rather than considering BAO, what we consider is the UBU splitting. So it's very similar to what I showed you in the previous slide, except the only difference is that we actually combine the A and the O. So the B remains the same in the BUB splitting, but what we now do is combine A and O to call or denote this by U, where this can be integrated exactly. And if we do this, then what we have is a splitting scheme which can either be referred to as UBU or BUB. And the advantage of using these methodologies compared to the previous one is that they are strong order 2 accurate. So this gives us further incentive to actually use these schemes when we want to discretize the stochastic differential equation. So this is the exact scheme that we're going to use, which I refer to as UBU. And what's also very interesting, which is given at the very bottom bullet point, is that the step size stability threshold depends on M, which is related to the strong convexity assumption, and also gamma, which is this friction term that you see right here. But despite this, it is independent of dimensionality. So because of these reasons, this is why we are going to use this UBU scheme in our unbiased estimate. So we can consider this for exact gradients. We can evaluate the gradient of this functional given by U exactly, but to take motivation from the machine learning community, which people are doing quite considerably now, is to consider inexact gradients. So you can consider different forms of inexact gradients. To give you the most basic example, which many of you know, is stochastic gradients. So what we do with this work and this presentation is that we're going to consider two different forms of inexact gradients. The first form that we're going to consider is a stochastic gradient variant, which is given by this very first equation that you see right here, where you can think of this as being very similar to the notion of mini-batching, where you don't evaluate or you don't consider the full gradient, but you consider a random subset of this, where the random subset of this comes from this omega that you see right here. So if we consider this stochastic gradient variant of UBU, then what we are able to show is that UBU with this particular scheme is of strong order 3/2. So that's for the case of stochastic gradients. And the second form of inexact gradients that we consider for this is what I refer to, or is what we refer to as an approximate gradient, which is a quadratic approximation of this. So we're interested in the quadratic approximation of x conditioned on x hat, where this x star you see is essentially the minimizer related to this Hessian term that you have. So this is just given by the approximate gradient. And if we consider the approximate gradient, then what we get is that we are able to show that UBU with this particular gradient scheme has strong order 1. So the motivation behind this is to improve on computational efficiency when we run these experiments, at least for high dimensional settings. It makes more sense than rather than consider the exact gradient. So far I've given you a lot of preliminary material before actually defining what the unbiased scheme is. What I want to discuss now is a very important concept in Markov chain Monte Carlo theory, which is metropolization, or the metropolization step. As I said at the very beginning, the idea of MCMC is that you simulate an ergodic Markov chain, and related to this, you have an acceptance probability. So you propose moves in your state space of your Markov chain, and you have an acceptance probability related to this move. From this acceptance probability, you have a particular criteria for which you say it either moves to that new state or new position in the state, or it remains the same. And so this is governed through the metropolization step, which is what I refer to as this acceptance criterion. So if we consider just the kinetic-based Langevin stochastic differential equation without any form of discretization, it has this invariant measure, as I've mentioned here. But if we consider a discretized version, dependent on these splitting schemes, or if we consider these inexact gradients, then we can't exactly get this in terms of the convergence to the measure, or to the correct pi. But what we can do to actually overcome this issue is that we can apply a metropolis hasten step, or in other words, an MCMC step, and indeed what we will get is exact convergence to the stationary pi, measure pi. Okay, so common examples of this in the context of Langevin-based stochastic differential equations include MALA, which is the metropolis-adjusted Langevin algorithm, HMC, which is the Hamiltonian Monte Carlo, and RHMC, which is randomized Hamiltonian Monte Carlo. So these are just well-known methods in MCMC which govern proposals. Okay. However, even though you have this, there is an issue which I mentioned on the second slide, which is this notion of the curse of dimensionality. In other words, you have to do some correct scaling with respect to some parameters to avoid your acceptance probability going to 0. What you don't want is your acceptance probability going to 0, implying that you just reject, or going to 1, meaning that you accept always. So what you ideally want is an optimal step size, which depends on how you tune your MCMC method, and that's related to dimension-dependent step size restrictions. Okay. So what I'm going to show you later on is the main methodology in a few slides, which I'm going to propose with this, which avoids the metropolization step completely, and where we can get very favorable theoretical results given through this table that you see right here. So the method that we introduce is called UBUBU, and why it's called UBUBU is because UB denotes unbiased, and UBU is the UBU splitting order scheme. Okay, so this name worked very nicely actually when we consider the UBU splitting scheme. And if we compare this to the other algorithms that I've mentioned above, MALA, HMC, and randomized HMC, what we have are complexity results related to gradient evaluations given here, and in terms of the conditions that are required in order to ensure that we have them. If we consider MALA first, if we have the condition that H scales related to d to the minus a half, then the gradient evaluations required for MALA is given to d to the half. And similarly for HMC and randomized HMC, what we require are different conditions where we have slightly better scalability in terms of d to the minus a quarter. But what we require is a Gaussian target. In other words, that is the pi that we are interested in. And as well as this, we require a warm start. In other words, the warm start related to this burn-in period. So provided you have a warm start, provided that you're interested in a Gaussian target, then given this condition, we have this complexity result for RHMC, which was provided by, I think, Simon Appers back in 2022. But if we consider our method, which is called UBUBU, we can get the exact same complexity result as randomized HMC and also HMC, except we actually remove these conditions. In other words, we don't require a warm start, and we don't require the fact that the only pi that we are interested in is of a Gaussian form. These are very, let's say, restrictive assumptions or conditions that one needs, but we can alleviate them completely just by considering our scheme, which is UBUBU. Okay. Before I discuss UBUBU, a very final slide that I want to discuss, which is related to the concept of unbiased MCMC. Okay, so with unbiased MCMC, we are interested in computing this particular quantity that you see right here. And the motivation behind this paper actually goes back to this work of Hamza, AJ, and myself in 2023, where we wanted to develop an unbiased estimator which avoided the metropolization step. So this paper avoids the metropolization step by considering this telescope and sum identity. And for anyone who is familiar with multi-level Monte Carlo, this is the exact main formula that you need for multi-level Monte Carlo, where if you're interested in computing some quantity, or if you're interested in generating samples from pi, this may be quite difficult. So what you can do instead is that you can have a very high resolution approximation to pi, which could be, for example, pi h, okay? And so if you consider pi, then what you can do is decompose this into a telescope and sum, which is based on this high resolution approximation that I mentioned before, given through these differences that you see right here. So in that paper, if they consider this particular step size, where you have different levels of discretization, so h of L equals h of 0 is just some base step size, and 2 to the minus L, as you increase the number of levels, what you should get is that the variance should reduce or decrease. And what you do get is an unbiased estimator whose variance is also finite. And the way that they did this is based on the ideas of Pierre Jacob. In other words, what happens is that from this work, you have to couple two Markov chains. They have a particular meeting time, and then eventually they will remain the same. So that's based on the theory of Pierre, which he describes a number of years ago. And because we consider a multi-level scheme related to this, what we are going to have is 4 chains as opposed to 2. Because we have the 2 couplet chains, and we have these at different levels of discretization, levels L and levels L plus 1. So this is one particular issue that we have. So because of the 4 chains, because of the fact that we only consider an Euler-Maruyama scheme, and also considering the fact there is a considerable lack of theory in this paper, this is exactly what we wanted to do in this paper that I'm discussing. Present more theory, more considerable numerical experiments, avoiding the use of 4 chains, and also using more advanced discretization schemes. So our proposed methodology, well, I'm going to copy Daniel and go straight to the diagram because I think that's the easiest thing to do first. So this diagram gives you a more easier representation of what I'm trying to do. So as I mentioned, we have different levels of discretization, and the idea is that as you increase these levels, the bias in terms of the burn-in bias should go to 0 as L goes to infinity. So if we consider the base level, which is level 0, okay, at level 0, what we have is the step size given by h of 0, where we have this burn-in period, which I denote by b of 0, and we have these number of samples given by k. And we have these parallel copies, which we have at level 0, so n copies at level 0. So remember, what we have is this, and then if we are interested in going to the next level, which is level L, what we do instead, which is different to the previous scheme that I mentioned by Uzakat, that instead what we do is actually increase this burn-in period that you see right here. So we increase this burn-in period by a factor of b, and as you continue for higher levels, going to level 2, 3, and 4, what we do is that we increase this by a further factor. And as I mentioned, the idea behind this is that as we increase the burn-in period, and as L goes to infinity, the bias of this will eventually vanish. So this is different to the previous method that was described here, which didn't consider this, but just essentially used the notion of this telescope and sum. Okay, so that's one key difference. Another difference is that we keep the number of samples fixed as opposed to the previous method, which was random or changed within each level. So this is another difference that we have as well. And so with this, what we do is that we define the approximate version of pi h of L given as this. So all of the approximations that we consider related to our new telescope and sum are essentially empirical averages. So we consider expectations of f, which as you see right here, which are governed by empirical distributions. So that is the key difference that we have between this telescope and sum and the previous one. Of course, there has to be some level of truncation in terms of the numerical experiments. But once we do this, what we have is essentially this final estimator that you see right here, S of L, L plus 1. And if we take the expectation of this, then what we can say is that this is an unbiased estimator of our. To give you an idea of how the actual U-Bu couplings work, what we've done in this experiment is that we've aimed to target a Gaussian target distribution where we consider a U-Bu discretization, different choices of the step size. So here you see on the very left-hand side figure, we have the coupled sample paths for step sizes given by h equals 1.5 and h equals 0.75. So relatively speaking, these are quite high step size to consider, at least for the case of 1.5. But as we consider this, we can start to see that they are relatively similar. They're not indistinguishable by any means, but at least they are quite similar. And this is quite promising, at least because these are high step sizes that we are considering. But if we half these step sizes on the right-hand side figure, where we consider h equals 0.75 and h equals 0.375, what we start to see are them becoming significantly closer to each other. These coupled sample paths are coupled because we are using a notion of synchronous couplings, ensuring that these paths are coupled through the corresponding same Brownian motion. So that's why they look very similar, but the difference here is that we have just a modified choice of the step size. So as we decrease the step size, as we go through further levels in this diagram scheme that you see, we start to see something that goes from this, where there is a bigger difference in terms of the coupling, compared to this, where we see a smaller difference in the coupling as well. So to give you an overview of the U-Bu scheme, I've given this bullet point scheme, which will hopefully help you understand this more easy. So at each level L, the Markov chains that we have are based on U-Bu discretizations with two step sizes given by h of L and h of L plus 1, just as I've given here. And they are coupled synchronously. And as a result, the variances, as you can see, will also be reduced as a result. So the strong order 2 property of U-Bu that I mentioned previously means that this difference that we have here is given by order h of L squared, and our estimator overall, again, is just given by this. So there are a number of technicalities in terms of how you actually present your algorithm or in terms of the parameter choices. I'm going to alleviate any sort of discussion related to this. I'm going to avoid it just because of time constraints, because I've got, I think, 8 minutes left. But if anyone is interested, I can discuss this later on. Okay. So finally, I'm going to show you some of the theoretical results before showing you some numerical results at the very end. The paper is quite lengthy. There are a number of analytical results related to the paper. I'm only going to show you 3 results related to this. One, which is related to the contraction, Wasserstein contraction, and the other 2 results, which are related to a central limit theorem. So we have a number of assumptions in order to ensure that our theory works, but at least for this theorem, we only require some of those assumptions. And those assumptions are given at the very top, where we have to assume that the potential U is M strongly convex and is capital M gradient Lipschitz. So yeah, I got confused between both M's previously, so sorry. So those are the 2 assumptions that we require. And we also require that A, B, C2, and C are some constants, which are given through these parameters that you see right here, where again, H is the step size, M is related to this assumption, capital M is related to that, and gamma is the friction term. So we let pH denote the transition kernel for a step of U-Bu with a step size given for H. And then for all of these conditions you see right here, we have this formula, which essentially states that we have Wasserstein contraction. So contraction is a very important entity that is required in order to show convergence of our particular scheme. In other words, the U-Bu scheme, okay? And the way you do this is that usually you would decompose this into a convergence bias and also a numerical bias. And then what we have is this particular result right here with this red that you see right here. So this is what we have. But just to say, I believe we also extend this to the case where we have inexact gradients, both in terms of stochastic gradients and approximate gradients. This result that you see right here, I believe, is only for the case of exact gradients. So that's the first result. The second result that I'm going to show you is a central limit theorem. So there are more assumptions. That's why I say suppose various assumptions. They can be found in the paper, but I believe, yeah, I'm not going to state those assumptions for now, but suppose that you have various assumptions which hold, and also further assume that you have these conditions. So if you look at all of these conditions, I believe I've introduced all of the notation previously. The only notation that I haven't introduced is this constant, which is a constant which I believe bounds the Wasserstein distance between your initial distribution and your target distribution. So I believe that distance is bounded by c mu 0 multiplied by the square root of d over m, little m. So assuming that you have these conditions, then what we can say is that our scheme, the U-Boo-Boo scheme, is finite variance and is also an unbiased estimator. Moreover, it satisfies a central limit theorem as we take n to infinity, where we have the following asymptotic variance bound. And the way that we did the asymptotic variance bound was largely based on this by Jourdain, who looked at concentration results in MCMC, where I think we used typical concentration inequalities, such as the Gaussian inequality, as well as the F-Ronstein inequality. So the point really that I want to highlight from this is that if we consider U-Boo-Boo, what we have is this dependence on the dimensionality. In other words, dh0 to the 4. So this is what I refer to, or this is what I mean, correspondence to this condition that we have. So we have to scale h of 0 to d to the minus a quarter to ensure that we actually cancel this term out. But more interestingly, we have another result which is very similar, which is to say that if we consider only product distributions, which include a Gaussian distribution, then if we consider the asymptotic variance, as you can see from the bound on the right-hand side, we have no notion of dimensionality, which implies that if we have product distribution that we're interested in targeting, such as a Gaussian, they are completely dimension independent. So this is very different to the case of randomized Hamiltonian Monte Carlo, which is that if you have the condition of a Gaussian target, there is still some dependence related to the dimensionality. And I'm going to show you this numerically to verify this result. So this is the result that I'm going to show you in terms of numerics. We are interested in targeting a Gaussian distribution, which is given by pi of x, in particular, a Gaussian target with eigenvalues of the precision matrix, so just the inverse of the covariance matrix, which are given through this this expression that you see right here. So in these two figures, I'm considering different cases for the condition number, where I consider kappa to be 4 and kappa to be 100. And what I'm testing is the dimensionality on the x-axis against the maximum gradient evaluations you need per effective sample size. So what I mean by a per effective sample size is the number of samples you need for an independent sample or to get independent sampling. In other words, to remove this correlation that you have. So I'm comparing these two in the context of randomized Hamiltonian Monte Carlo and U-Boo-Boo. If we consider the case of randomized Hamiltonian Monte Carlo, if we consider 10 to the 1 dimensionality, we have something which looks like this. But as we increase the dimensionality all the way to 10 to the 5, we start to see that this does have a dependence on the dimensionality. Now, this is different to U-Boo-Boo, where if we consider U-Boo-Boo, this remains fairly constant related to the dimensionality, which is very nice. And if we consider a higher condition number of kappa equals 100, we start to see a very similar phenomenon where we do indeed get dimension independence for U-Boo-Boo, but for the randomized HMC, for a Gaussian target, we do not. And this is another example if we just consider an alternative test function given by the norm of x, where we start to see that with randomized Hamiltonian Monte Carlo, this is just the interpolation through the points. Again, it is dimension dependent, but with U-Boo-Boo, it's more constant, considerably more constant, so independent. So given that I have 2 minutes, I'm just going to quickly show you this Poisson football model. Just to say, in the paper, we also have an MNIST regression problem, which is very interesting as well. I have limited time, which I knew beforehand. That's why I'm only going to show you the results and not present the details of this model. So we consider a Poisson football model, which is essentially a random effect model. And what I'm comparing here, again, is the gradient evaluations per effective sample size, comparing U-Boo-Boo, approximate U-Boo-Boo, and the randomized Hamiltonian Monte Carlo. If we consider RHMC, first of all, we have that what I really want to point you to is this box, which shows you the minimum gradient evaluations per effective sample size and the maximum. And if we consider RHMC, then the maximum gradient evaluations we need per effective sample size is approximately 1600. But if we move to the U-Boo-Boo scheme, then already we can see if we consider the same metric, which is the maximum, we only require 55 gradient evaluations, which is a considerable difference compared to the RHMC. And if we move to the approximate scheme, then what we get is only 2 gradient evaluations per sample size. So implying that we have an even more considerable difference if we consider inexact gradients. We also get similar results for the MNIST regression problem, but they are not as significant as these results. That is the reason that I decided to show this, where we haven't showed the stochastic UBUBU for this example, for the MNIST one. So given that I only have 1 minute, I don't think I'm going to go over this slide. This is just to summarize what I've done. Here are a number of future directions that we can consider for this work. Just to say, if one is interested in the non-convex setting, Peter has a very nice work which was recently archived. If anyone is interested in this, this is the paper with the archive link. And with this, I conclude my talk. So thank you.
Are there any questions? Oh, that was joined. Robert,
Okay, yeah, thank you for the talk. You showed these nice dimension independent plots, right?
Yes.
You mentioned in the beginning that in your multi-level strategy, you now have this burn-in phase, and given on the level, you kind of extend this burn-in phase. So first question is factor in how much you increase the burn-in.
Can you repeat the question, sir? How much?
You have some factor, how much you increase.
Yeah, B0 plus B.
Exactly. You make it so this is just, and this factor, this B, is this dimension dependent?
It is, Daniel, is it? No, it's not dimensional.
Even the burn-in phase is not dimension dependent.
So in practice, no, it doesn't depend that much. Yeah, so yeah.
So it implies in the last plots when you measured the gradient evaluations, this includes the burn-in phase or not?
is the speed just a hyperparameter for these features?
The speed is controlled by the contraction. Normally, the contraction does not depend on dimension. The dimension comes in when you try to match the bias.
Thank you.
Maybe I've just had my question answered, but I just wondered what's the interpretation of the bimodal distribution you see in the gradient evaluations per ESS, but now I'm thinking probably it's the burn-in phase. So
Also,
I think it's more related to the eigenvalue structure of the Hessian or like if you know some, because what these plots show is like each individual component. So if it's like has a particular eigenvalue structure in the distribution, then that will be maybe related to the efficiency a bit.
Okay. Any other? Oh, Laura, yes.
Yeah. When you're proving your contraction, so you said let CH equal. Yeah. So how do you derive the CH?
you would know this, I think.
Well, I mean, this agrees with the sort of continuous analysis, but I mean, it just sort of comes out of the analysis, I think. Yeah. I mean, once you try and prove these contractions, like you use the same noise and then you consider the inequalities, this is the constant you need in this high friction regime.
Like, was it like you found one that worked and then with that found that it
Sorry?
where you like fix it at the start and then show that it worked?
I mean, yeah, there's already results for the continuous analysis, so you can just fix it at the start and then prove it. But I think you end up with some linear algebra problem, and I don't think you can get better than this for the UBU.
The question from the question?
Yeah. Can you go back to the slide where you kind of motivate the comparison you want to make between the what you call unbiased kinetic Langevin and randomization? This one, yeah, thank you.
Yeah.
Yeah, I really didn't get what you meant in this slide in the sentence.
Just a little bit.
Yeah, I didn't really get what you meant in this slide when you aim to compare things. So there are different processes, but there are also different methods, right? The three first method, they use metropolis correction, but your method doesn't. So what is the main purpose? Is to use a multi-level Monte Carlo, is to use Langevin? That's the for me, it's not so clear what you're trying to compare.
So we're trying to avoid the metropolization step completely,
Okay.
which was first done in this paper.
Okay.
We also want to demonstrate non-asymptotic results compared to those methods, at least theoretically, to get an idea of how it works. And also we want to numerically test them. So I think maybe I should have shown this table on a different slide because yeah, this is